All right, so I wanted to go ahead and get started on the rest of these IB problems. So here's question number 5. So we're going to be moving from conservation of energy into some of the IB work that we're doing in the subsequent problems. So we've got a mass, and it's going to explode into two pieces. So we've got this 10 kilogram mass here. And what happens next is that we've got this 4 kilogram piece that moves at 6 meters per second to the left. Excuse me. And I didn't tell you this, but if the total mass is 10 kilograms, it follows that this piece has to be moving to the right at an unknown speed. So we want to know the velocity of the second piece, and for that, we're going to use conservation of momentum. So we're going to have 10 kilograms moving at 0 meters per second, and then we'll have 4.0 kilograms moving at negative 6.0 meters per second, because remember, left is negative. And then we're going to have a 6 kilogram piece moving at its unknown V final. So when we actually simplify this, we're going to end up getting that V2 equals 4.0 meters per second. Now the initial kinetic energy of the system is going to be 1/2 times 10 times its initial speed squared, which is 0 squared. So we're going to get 0 joules initially, or 0.0 if you want to do it that way. Now the final kinetic energy is going to be given by the kinetic energy of each individual piece. So we're going to have 1/2 times 4.0 times negative 6 squared plus 1/2 times 6.0 plus 4.0 squared. So kind of continuing this here, we're going to get 72 here plus 3 times 16, which is going to be 48. So we're going to end up getting a total of 120 joules of energy in part C. So where did this energy come from? This energy came from, you can see it came from the explosion. And if you want to know where that energy came from, it came from the chemical bonds, the chemical energy of the explosive. So there's a chemical potential energy that we'll actually get to when we deal with electrical energy and some of the stuff from later this semester and into next year. So that's question number 5. Now, I want to give you a few hints here. So here, we are going to be using conservation of energy once again. So an object falls in a vacuum. It's got gravitational potential energy. We want to know the speed of the object. So we can have E initial equals E final. Our initial energy is E. Our final energy is all kinetic. So that word speed lets me know that. So we have 2E over M equals V squared. And when we isolate, that's how I'm getting choice A. Now, for number 7, these comparison problems, you've got basically situation 1 and situation 2. So let's look at situation 1. Situation 1, I've got kinetic energy 1/2 mv squared. Now situation 2, I've got half the mass and twice the speed. And now I just clean it up. So I've got m over 4 times 4v squared, which gives me mv squared. And now I compare. I'll take a ratio. So ek2 over ek is going to equal mv squared over 1/2 mv squared. And when I simplify that, I'm going to get that ek2 is twice ek. And that's how I'm getting choice C. The reason I had you do number 5, so C number 5 on the homework. The total momentum is unchanged, the kinetic energy is increased. That's how I get choice A. So C number 5 on the homework. There was a reason that I had you do this problem right here. Okay. And in fact, I'll even write C number 8 on homework, just to kind of let you know how it applies. And then question number 9. Here, wow, this is an interesting one because we know that power is work over time, which is force times distance or displacement over time. And then we do a little trick here. We factor force times d over t, and this in parentheses is the velocity, so that's how we're getting power. And then here, we have a particle moving in a circular path and we want to know the work done. This is an interesting question because we're actually going to use work as the change in kinetic energy. So check this out. I've got 1/2 mv final squared minus 1/2 mv initial squared, and that's going to be 1/2 mv squared minus 1/2 mv squared. The speed is the same, so this actually equals 0 work done. In general, this is one of their favorite questions, and just so you know, whenever you see something move in a circle, assume that the work done is 0. Now here, the heights. We got height, height, and height. Here's the deal. If you start from the same height and there's no friction, you're going to end up with the same speed regardless of the shape of the path. Now, the time to slide may be different. I suspect that this is the shortest time, this is the middle time, and this is the longest time to slide down. That's what I suspect. But as far as the speed goes, all that matters is how high did you start up from. That's it. Now for 12. This, you know what, I'm not going to give you all the hints, but just know that work is the area of this graph, so I'd use a triangle. And then here you've got power, so I would start with this formula for elastic energy, and then also use that power is work over time. There's your hint. Okay? So hopefully this will help you with 12, 13, and the others, and those should be those are the hints that I want to give you for the homework that's due on Friday.